Alright, kia ora everyone. Here's your final lesson for the week 7 lockdown work. This might take you a little bit longer than the other lessons because I am going through quite a few calculation examples, so hopefully you've decided to start this a bit earlier. But feel free to pause at any point and just kind of take a break because I know it'll probably be a lot, but I'm hoping by showing you all these different examples you'll be able to tackle any sort of question. Alright, so for today we're going to be processing how to use that heat change values that you calculated in the last lesson to then use that information to calculate enthalpy. So basically, we're still working with that enthalpy material and that using that heat capacity material for the water. All right, so here is our next equation that we need to look at, which is your delta H, so your enthalpy of that reaction. That is equal to the negative Q value. So negative Q value, the Q is obviously representing the energy, not the energy, the heat energy that you calculated in the last lesson. And then you will divide it by the moles of the chemical reaction. And from there, you can get joules or kilojoules per mole. So, 4 different examples, sorry for you guys, but hopefully you'll get an idea of what I mean. This first example is just a straightforward one, just so you can see this new equation, and then the other two are showing you how to integrate those other three are how to integrate those 3 different examples together. Actually, from memory, one of these you guys have done previously, yeah, so let me just put that into the notes before we start talking. Cool. All right. I just wanted to move that so that way we got a head start at least on one of the questions. Okay. So, like I said, same sort of setup that I've done before. We will write our knowns, our unknown, and then our equation slash working that we're going to be doing. So, in this example, I am just showing you how to use that delta RH equal to the negative Q divided by N equation is all that we're focusing on. But in reality, you're actually going to be integrating those 2 equations together. So, calculate the energy released if you have dissolved 10 grams of the sodium hydroxide, and they've given you the equation, and they've given you the delta H value. So actually, in this case, what I'm solving for is energy release, so I am actually solving for the Q value in this example. Something they can ask you to do, it's just basically you rearrange the equation. For my knowns, I know my mass, which is 10 grams. I obviously now need to convert this into moles. So I'll do that in a moment. And then the other thing I know is my enthalpy value, which is negative 20.6 kilojoules per mole. Just running out of space there. So first thing I'm going to do is I'm going to convert this guy into moles. The way I do that, if you guys remember, is that moles is equal to mass divided by the molecular mass. So I am doing 10 grams, and I'm dividing it by the molar mass of the sodium hydroxide. Now, that, if I quickly look that up, which I should just look up sodium because I know the other ones. So sodium is 23, the oxygen 16, and the hydrogen is 1. So basically, I am working with 40. So divided by 40 grams per mole. The grams will cancel out, and I'm left with per mole, which works out because that is the unit I want to try to get to. So 10 divided by 40 equals 0.25 moles. So that's what I can plug in here. N equals 0.025, not 0, just 0.25 moles. All right, cool. Next part of the equation then is that I want to find my, not my Q value. No, yes, my Q value. What am I talking about? We do want to find that Q value today. So we are going to be rearranging this equation to solve for that. So you can either rearrange the equation to start with, or you can plug in your numbers and then rearrange it. So if I'm thinking about that equation, I want to get Q by itself. So I'm multiplying both sides by n. That'll get the n's to cancel, and then I basically have negative Q is equal to n times your delta H value. Basically what this means is whatever I get Q to be, I just need to take the opposite sign of it. So this is going to be a mess. Negative Q equals 0.25 moles times negative 20.6 kilojoules per mole. So again, you can see I'm writing down the units to make sure those cancel out, and that way I figure out my kilojoules. So 0.25 times negative 20.6, so I get negative 5.15, but if I do the change in that symbol, it's going to actually be positive 5.15, and that's kilojoules. And that's my final answer. It needs to be in 3 significant figures, and that's what we're looking at. So we can manipulate this equation. And we could actually manipulate this even further. I could go back to that Q equals M mass times temperature change times the latent heat of water, and I can actually backtrack and figure out the temperature change and stuff like that. But obviously I don't have enough information in there for me to do that because I don't know the mass of the water that the sodium hydroxide was dissolved into. So that's just a simple example of us being able to rearrange that equation and use it. In the second example, it's basically looking at the one that you did yesterday. So yesterday, if you guys remember, we were looking at this question and we basically could find the Q value here. Now we're going to take that experimental data information and we are going to figure out the delta H of that reaction. I'll just zoom it out so you can see all of it. There we go. All right. So thinking about my knowns again, I now know my Q value. And I'm going to keep it in kilojoules. I realize now that there shouldn't have been 2 periods there, 2 dots. All right. That's in kilojoules. What else do I know? Now, I want to calculate the enthalpy released from the 1 gram being dissolved. So this is where you need to be careful and when you're doing your conversions, because when I'm thinking about this and I want to figure out the N value, I want to figure out the mass of the amount of whatever is doing that chemical reaction. So I'm actually not going to be using this value when I'm doing that conversion. I'm just using that 1 gram. And I hope that makes sense. So when I think about the reaction, it's only that 1 gram that is actually dissolving. There isn't actually anything in there that has to deal with the water, other than the fact that it's the dissolving component. So if I wrote out this equation, that is the active component, is that dissolving. So that is what I want to figure out that delta H for. So the water doesn't come into play, and I'm only dissolving 1 gram of sodium hydroxide. I'm not actually dissolving 41 grams of it. So that's why you gotta need to be careful, and like I was saying, it's a real reading comprehension bit. So I need to take the 1 gram and divide it by the molar mass of sodium hydroxide, which is 40 grams per mole. That cancels out, and what I get is that 0.025 moles. So I hope that makes sense to why I was doing that. All right, I know the Q value, I know the N value, so now I am ready to solve for my delta H. So delta H is what I'm solving for in this next round. So I know that the delta H is equal to the negative Q value divided by the moles. So that will equal negative 0.54. I'm not good at reading numbers. That's the value that I'm getting, dividing it by 0.025 moles. All right, so let's do that. 0.41.025. All right, so delta H is equal to negative 20, and I'm going to now do my significant figures, 0.6, because I'm rounding it up, because it was 20.5656 kilojoules per mole as my final answer for that enthalpy reaction. Some things to just double check, just to make sure you're right. We see that this is a negative number, so that tells me it's exothermic. And when I look back at the question from yesterday, was saying that the temperature changing is going from 20 to 23. So that is an increase in temperature. That is also verifying that you have an exothermic reaction. So just check the signs to things just to make sure you have it organized the right way around. So that's taking that to the next step. I hope that you guys are okay with me just kind of jumping ahead like that, because you've seen the first half yesterday, or in the previous lesson, I should say. All right, cool. Let's see another example of this. So another example of this is you are mixing solutions together. This is often called the enthalpy of neutralization, and that's how you'll see it referred to in the SciPad. But basically, it's saying you have these two solutions that you've mixed together, and we want to figure out the, again, enthalpy change. Now, I can't do that right away because I need to first figure out the heat energy, and then I can figure out the enthalpy. So let's start with my knowns and my unknown, and then my equations / working. Now with the unknowns, we're actually going to have two, because there's going to be two steps to this process. So here are the things that I know. I have sodium hydroxide, and I have hydrochloric acid, and I'm doing 50 mils of each solution. So if I want to think about the mass of the water that I'm using, 50 times 2, because I'm mixing two solutions, that's going to be 100 grams. So that's the first thing I want to kind of point out to you guys, and I hope that's okay and logical when you are thinking about that. Both solutions are 1 molar. That's going to be important when I'm figuring out my moles. And I'll talk about that in a second. The next thing is my temperature change. So I see that the temperature change from this example here is 32.2, and we subtract 25.5. So that is an exothermic reaction, and my temperature has increased by 6.7 degrees Celsius. So that's my next component there. I know that my C is that heat capacity, and that's going to be constant. Sorry, that should be an 8. Joules per gram per degree Celsius. Now, I can keep working if I want. I can go from this information and keep going, or I can add this 1 mole solution. I'm going to probably solve it first with the steps of what I have information-wise, so that way, hopefully, when you see how I figure out then the second equation, I know I can show you then why we're doing what we're doing with that. All right, so going back to it, I need to find my Q as my first thing. Q is equal to mass times the temperature change times C. So Q is equal to 100 grams times the 6.7 degrees Celsius times 4.18 joules per gram per degree Celsius. So let's figure that out. 100 times 6.7 times 1.8. And I get my Q value to equal 67418 joules. Now I can use this number for my second part. So I'm going to put that down in there. That's my next new information that I have figured out. Cool. All right. We are thinking back to that other equation we were looking at, which is the delta H. So I know I'm doing something with delta H equals negative Q divided by N. I can't use that equation quite yet because I need to know what N is. So let's go back and do another step. In fact, this is basically 3-step calculation. So when I think about N, I need to think about what is the chemical reaction that's occurring, not how much solution or liquid is there. Because the liquid amount I'm thinking about, because I'm thinking about, okay, what's the heat capacity of water? So basically, you're just asking how much water has been heated and changed. When you are looking at the enthalpy, you're looking at the reaction that's changing the temperature of the water. In particular, I'm looking at the hydrochloric acid and the sodium hydroxide. So I'm thinking about sodium hydroxide plus hydrochloric acid forming water and salt. So that is what I am thinking about, and that's what I want to figure out as my delta H value. So basically, we now need to figure out how many moles were involved in that reaction. Now, the good news is this is a 1-to-1 ratio, so neither of those two things are going to be a limiting factor, and I only need one of them. Basically, you want the one that's going to cause the limiting factor of the reaction. What's going to run out first, mole-wise? In this case, since it's a 1-to-1 ratio and both solutions are at the same concentration, there is the same amount of moles for each one of those reactants. And usually they'll give you that to make your life easier. Otherwise, you'd be doing both the calculations and you'd figure out which amount do you have less of, because that's going to be the factor that limits you. So, thinking now, we are going to be using the equation that concentration is equal to N divided by the volume. So we rearrange that N equals concentration times volume. Now I have that concentration value. So C is equal to 1 mole per liter. I also have the V amount because I know there were 50 milliliters of each solution, which translates to 0.5 liters. So that's what I'm doing for that amount. I'm doing N is equal to the concentration times 0.05. Let's put down our unit. So that's moles, and that's moles per liter. I'm running out of space there, but the moles cancel out. Sorry, I'm doing something wrong. Let me actually put the space in properly. All right, so concentration, I have 1 mole per liter, and I'm multiplying it by 0.05 liters. So the liters will cancel out, and then I will get mole by itself. That's why it's important to write down units. It's a good way to double check yourself. So 0.05 moles. So now I can add that to my list of things I know. N equals 0.05 moles. Now I can figure out delta H because I can plug that in. So the Q value that I had is this one here, and that's negative. So negative 674.18 joules divided by this value here, 0.05 moles, because that is the amount for that reaction. Cool. I get an answer that is 13,483.6, and that's joules per mole. Let's divide that by 1,000 to keep that as kilojoules per mole. So that's going to be 13.4836 kilojoules per mole. But I want to get my delta H into a nice 3 significant figure number. So delta H in this reaction is going to be 4 rounds up to 5 kilojoules per mole. So that's the answer to this one here. Try to make it clear for the examiner where your answers are. Cool. So that's the next example. I hope that makes sense. So just kind of keep in mind when you're reading how you're pulling the information. So in this first example here, we were looking at dissolving something into water. And when we dissolve something into water, we're looking at the grams of what you've dissolved for your moles in that second equation. For this one here, we're mixing two solutions together. So I'm looking at the concentrations of the solutions and the amount of the solution I have added. I'm looking to see which one is the limiting factor, and that's what I'm using for these calculations. This question is tricky because you're going to have to do lots of reading comprehensions and pull the right numbers for the right reasons. So I'm hoping by giving you 3 examples, you know what I'm talking about. And there's plenty of practice in the SciPad. All right, this last one is probably my favorite one because I think it is a really good example of how you need to really read carefully. So this is one you haven't seen before. In this example, we have alcohol that we are burning. That's releasing heat energy, and we're measuring the temperature change of the water. They then want you to backtrack and figure out what is the enthalpy of the combustion of that alcohol. So that's what you're working with. Anyway, let's go through and process it. Let's write down our knowns. Let's write down our unknowns. And let's write down our equation and our working as we're going through it. And I'm trying to change color so that way you guys can kind of see the steps. All right, so first thing, we have a tin can containing 200 milliliters of water. So that's that right there. So that tells me the mass of the water is going to be 200 grams. I need to know that as my starting point because I know I need it for that Q equation. All right, the initial temperature of the water was 22 degrees Celsius. So that is mass of water. That is the initial temperature. So we're going to go T with an I. The spirit burner had a mass of 484 grams when it was lit and the heat was used in the can. Once the splint was extinguished, the temperature of the water is now 27 degrees, so that's your final temperature, and the mass is at 184.3. So both of these are referring to mass, but in this case, this is the mass of the ethanol. I think it's ethanol. Yes. So basically you're saying this is how much ethanol I have burnt, and that's what's going to be converted into your moles because you want to figure out the enthalpy for the combustion of the ethanol. So let's write down more information that we have. We know that my temperature change is 27 minus 22, so that's a 5 degrees Celsius temperature change. I know what my C value is. What am I doing? That's the wrong units. So that is joules per gram per degree Celsius. The other thing that I know is I know the mass of my ethanol. So the mass of the ethanol is equal to 184.5. And we're subtracting away 184.3. The reason why I'm doing that subtraction is because that mass change tells me that I have used up 0.2 grams of ethanol with that burning. And I hope that makes sense to everybody. Cool. Obviously, I'm going to need to know some things. So if I'm thinking about what I need to know, in my final equation, what we are thinking about is, just trying to think what's the best way to show you. Yeah. Delta H of the combustion of the ethanol. Actually, I don't want to write all that. Let's just keep it simple. So I want to know the delta H. That's also in the wrong order. Hold on. There we go. Delta H of the ethanol is what I want to figure out. So I need to have the Q value to do that, and I need to have the N value to do that. That's the final equation I need to do, because this will tell me the combustion of ethanol. So to my list of unknowns, there's 3 things. First off, I need to know what my not first off, the final thing I want to know is the enthalpy combustion for my ethanol. That's my final answer. In order to do that, I need to know the Q value. I also need to know the N value. I can do both of those things because both of those things, I have that information there. So let's start with the Q value. So Q value is equal to my mass times the temperature change times the heat capacity of water. Now, when it comes to the mass that I want the mass of the water because that is telling me the energy that must have been absorbed by that mass of water. So Q equals 200 grams times 5 degrees Celsius times 4.18. Cool. So hopefully that makes sense. So now I get my Q value. So just be really careful with what numbers you want to grab. So I want to grab the temperature change of the water. So that's why I'm grabbing the mass of the water. All right, so that's 4,180 joules. So we'll add that to my list of information that I know. All right, other thing I now need to know, I'm going to do this in gray actually, is I need to know the moles. So N equals the mass divided by the molecular mass. Now, once again, I know what the mass is, and I want to take the mass of the ethanol because that's what's burning and that's what's doing the chemical reaction. The only thing that's then missing is the molecular mass. Now, molecular mass I can figure out by looking at the formula that I've given. So I have 2 carbons, so that's 12 plus 12, that's 24. I have oxygen, which is 16. And then I have 6 hydrogens. Hydrogen is 1. So I'm adding 6. So my molar mass is 46 grams per mole when it comes to that ethanol. I'm writing that all wrong. I'll just put it over here. Cool. All right, so now I can plug that in. So N equals my mass, which is 0.2 grams divided by 46 grams per mole. Grams cancel out. I have per mole, so that's looking good. And I have my amount is equal to 0.004378216 moles. So I can do that. N for the ethanol. It helps if you label things just so you know what numbers you're grabbing. So 0.00438. I'm just going to round it over here just to make my life easier. All right, so now I know those values. I'm taking this N value, I'm taking this Q value and plugging it into the equation that I had earlier. So the combustion is equal to negative 4180 joules divided by 0.00437. Use the long answer. All right, and that'll be in joules per mole. So let's take that answer. And I get combustion. I'm not sure if I'm putting the thing on the right spot. I didn't over there. All right. 961,400 joules per mole. We can convert that into kilojoules by dividing it by 1,000. So 961.4 kilojoules per mole in that case. And then 3 significant figures. So the combustion energy for ethanol is equal to, oh, that should be a negative number. There we go. Negative 961 kilojoules per mole. And I'm rounding it to 3 sig figs. Since this is a 4, I'm rounding down. Now, again, easy way to double check if you have the right answer. I see that I put a negative sign there. And I see that my temperature change was increasing, so that's an exothermic reaction, which is what I see when I do the delta H calculation. be careful and remember to check that, because this is a really frustrating question that, for my memory off the top of my head, if you can do like one step of the calculation, that tends to be the achieved. If you can calculate it, then you get a merit. But what they're looking for excellence is, do you have the symbol? So positive or negative, and do you have your units? And do you have it 3 significant figures? It's a real kind of silly, arbitrary thing that we want for an excellence, but it is what it is. So hopefully from those 3 examples, you'll be able to tackle any question listed in the follow-up work. The main thing is just reading comprehension and trying to pull the right numbers, because you're getting multiple numbers, you're dealing with different masses, and you need to just ask yourself, what is the water being heated for the Q equation, and then what is actually part of the reaction, and you use that for your enthalpy equation. So I hope that makes sense. Just move that back. All right. Again, if you did do that practical at home, now that you guys have this extra bit of information, you can actually take this one step further, and you can factor in the grams of sodium hydroxide that you dissolved. So that follows the first example, or first practical, example 1, basically. Not that one, this one. It follows this example. Because now if you know the mass of the salt you dissolved, you can convert it into moles, and then you can do the energy divided by the moles. And the neat thing about being able to do this is you can actually verify if it's right. So you can Google the enthalpy value for dissolving sodium chloride and see, does your number match what the standard, what the values are, because you have to remember that when we're looking at those values, they're done under standard conditions. So you can see, like, it should be 25 degrees Celsius, which is room temperature, 1 atmosphere pressure. You could also then verify, like, are you losing heat energy, or having, not losing, you could be gaining. Are you getting basically interference from the surrounding? So you can basically kind of test how good the cup is. So you can think, do you get the same answer? And then you can ask, why or why not. I kind of gave you the answer to that. That's okay. It's a cool kind of thing to do at home. All right, Kapai, that's everything for this week. So by the end of this week, you should be able to process how to use the heat change values to calculate enthalpy. For your follow-up, do the recommended tasks that I've listed for this lesson. There's also a CPR quiz as well, so make sure you get that done. Both of these documents are on Google Classroom. So give it a go. It's probably going to take a little while just to process. The more math problems you do, the better, because it'll help you just kind of learn the process of how to do this. All right, that's everything.